Thank you for coming, and thank you for hosting me and for these kind words. This is a talk I gave last year for the first time when I won the Eurogold medal that Alison mentioned. And they wanted something that would cover my career. And since I started my PhD in 1972, and last year was 2022, I thought I should have a title like 50 years of operational research. And so this year it would be 51 years, but it doesn't matter much. Okay, so this is the purpose of this talk. It's an overview. It's not a technical talk at all. It's a very simple talk. It's mostly pictures. But it tells you what types of problems I've worked on in the last 50 years. So I have chosen 10 topics. And it's like in the Google rankings. You know, I start with number 10, I go to number 1. So number 10 is the first one. This is the topic of my PhD thesis, which I did under the supervision of Alza Land. And the problem was called the Seriation Problem, and it has an origin in the ranking or the ordering of graves in cemeteries. So if you have a cemetery like the one on the left, and in these graves you find artifacts that people used to put over years. So they would put pots for 50 years, and they would put a jewel for 25 years, and that sort of stuff. And the idea is to induce a relative ordering of the graves based on the artifacts they contain. So that translates into a combinatorial problem with a 0-1 matrix, where the rows represent the graves, and the columns represent the artifacts. And you don't know the order of the rows at the beginning. And you'd like to permute the rows so that the ones over the columns are as close as possible. It means that you will suppose there are no interruptions as much as you can find in all the columns. So you want to minimize the sum over all the columns of the difference between the last one and the first one, so that would give you a kind of likely ordering of the graves. So in this solved example, you can see that some columns have gaps, but we try to minimize not the number of gaps, but the total length of the gaps. So this is the problem I worked on with my supervisor for the 3 years of my PhD. And I've got a few papers out of this, including one in Journal of Archaeological Science. So I started my life in archaeology. You can solve this problem by integer linear programming, but it's messy. You get very weak relaxations, and it takes time by using branch and bound to reach an optimal solution. You can use dynamic programming, but that's quite limited because the complexity of dynamic programming is O of n times 2 to the power n, where n is the number of rows. So you can go up to 20, 25, 30, I don't know, but there's a limit to what you can enumerate with 2 to the power n. The best way to solve this problem is to use various exchange mechanisms, but then you don't have an optimal solution. So basically, this is an unsolved problem if you assume that you want an exact, proven, optimal solution. Then I worked, when I finished my PhD, on what we call rotating schedules. So these are schedules used by people like policemen or some factory workers who work 7 days a week, around the clock. So they basically work 3 shifts a day, 7 days a week. So there's always someone working. And there are people who are off, and with an X. So if you look at this schedule, it's a 5-week cycle, and you distribute your workforce in 5 equal teams. And the first week, team 1 does the first row, team 2 does the second row, and so on. And after each week, you move to the next row of the schedule. And after 5 weeks, you go back to the top. And there are rules regarding the sequencing of the various shifts. You can see that here you work in the first week 4 times during the day. And after having worked 4 times during the day, you have 2 days off. And then you work 3 evenings, 2 days off, and so on and so forth. So, of course, you cannot have sequences of D and E and N together. You work on a certain shift for a certain time, and then you have some time off, and then you can go to a different type of shift. You don't want these shift sequences to be too short. You don't want them to be one. Because if you have a day off, you work, and a day off, you know what's going to happen? People are going to call in sick and say, I cannot work today. We've put all the nights together here, 7 nights, because when people work during the night, they don't like to work a little bit during the night, take 2 days off, and work again during the night. They like to do all the nights together, because when you take the days off between 2 night stretches, you don't take your days off during the night. So it's complicated. It's a jet lag problem. So we worked on this, and this schedule, by the way, is the one that was implemented by the police department in Montreal, and it's been like that for a long, long time now. So how do we solve this? You can use integer linear programming. It doesn't work well. You can use various heuristics. You can do the schedules by hand, which I used to do at the beginning, because it's not easy, not complicated to do that for a 5-week schedule. Or you can use constraint programming, which is the best tool for this type of problem. This is a longer schedule. It's a 12-week schedule, which was done for some transportation department employees. It's a little bit more complicated to solve, even by hand. And it shows some of the difficulties of solving these things. One thing you have to do when you design a schedule is to decide what's the length of a cycle. The previous one has a length of 5. It was a very simple schedule. This one is a 12-week cycle. So how does it work? Why should you take 12 weeks or 13 weeks or 10 weeks? Well, you have to work out how much you want your people to work. If you have a 12-week cycle, you can count here how many times you have a D, an X, not an X, a D, an E, or an N. These are the days when you work. How many days do you work? How many days are there in the cycle? Well, there are 84 days in that cycle. How many times do you work? And when you work, how long do you work? 8 hours? Normally 8 hours. So if you multiply the number of hours per shift, 8, times the number of times you work, and divide by 12, you end up with how many hours you work in a week. And you have to decide that before. You have to play with these things. Once you come to an agreement between the employer and the employees, then you can start making the schedule that satisfies the rules I gave you. Okay? It's an interesting process. I've spent most of my working life on solving various types of vehicle routing problems. This is what I'm mostly known for, I think. So if you don't know what a vehicle routing problem is, you have a central depot, you have customers, and you have to deliver quantities of something to the customers. And you have vehicles. You have here 3 vehicles. And these vehicles have a capacity. And you want to make sure that you have vehicle routes that satisfy the capacity constraint. You may also impose a length constraint. You may say, my routes cannot exceed 8 hours. You can have time windows. You must arrive at a customer at a certain time, or within a certain window, between 10 in the morning and 12 in the morning. That sort of thing. And there are zillions of other constraints that you can consider. So this problem is, first of all, it's a real problem. If you go on the street, you'll see vehicles. I don't know whether you call them lorries or trucks here, but you see vehicles that carry stuff, and they have to obey some of the principles I gave you. And the idea is to find a solution that minimizes the total travel time or the total travel cost or what have you. There are, as I said, many applications. There are many variants. And the problem with this type of work is that suppose I want to become rich. I want to design software that I will sell to companies to solve this problem. It's going to be tough in the sense that no two companies have exactly the same problem. So it's not one size fits all. You have to design a kind of software that can be modified or played with by the users. Because it's very rare that we get two companies with exactly the same problem. How do you solve this problem? Well, you can solve it heuristically, obviously. It's quite easy. Or you can solve it by mathematical programming. So this is the formulation we first proposed in 1985. It's the basis of all formulations, or most of the formulations that have followed. But this is based essentially on what you do for the traveling salesman problem. So you want to minimize the total routing cost plus the cost of your vehicles, subject to the fact that each node has to be entered and left once. So there's a degree of 2, except the depot, which has a degree of 2m. The complicated constraints here are connectivity constraints. It means that you cannot have subsets of customers that are isolated from the rest. So everything has to be connected with the rest of the graph. And the variables are integer 0, 1, or 0, 1, 2, those related to the depot. So this is a basic formulation. You cannot solve very large instances with such a formulation. In 1985, we went to 60 customers, which isn't bad. But if you want to add additional constraints and solve larger instances at the same time, this will fail quite easily. What people do is that they do column generation when the constraints are very tight. Especially when you have very tight time windows, you can use column generation. Or you can use branch and cut, which is what we did in 1985. Or you can combine both. You have branch and cut and price. So you can relax columns and you can relax rows at the same time. And this is the best methodology so far. You can solve instances of this problem exactly for about 200 customers, 200-300, but, there's a big but, you're not sure that your algorithm will always be able to do it. So there's a very high variance in the success rate. So you can have an algorithm which 3 times out of 10 will solve a large instance of 200, and 7 times out of 10 will fail after 7 hours of computing time. So it remains a challenge to solve this thing exactly. We have fantastic heuristics. The best heuristics that are available can solve instances of 500, 1,000 customers within 0.5% of optimality, more or less, which is sufficient for most people's needs. So essentially, this problem is solved. I don't believe that it's going to be easy to improve so much the exact algorithms, and the heuristics are good enough for our purposes, I think. You have to be careful when you design heuristics. either for this problem or other problems. Typically, you test your heuristics on a set of classical instances. And the danger is to say, my heuristic doesn't work well on instance number 5. So I'm going to add a patch to my heuristic so that instance number 5 will work well. And that's not the way to go. It's not scientific. You should have a heuristic that uses the same parameters, the same rules for all instances, and as much as you can for all possible variants. And this is the work of my colleague Vidal. One size fits all. Then you can move to the stochastic case of that problem. And in reality, everything is stochastic. So what is stochastic in the vehicle routing problem? The demand. If you collect things from customers, you don't know exactly how much they're going to give you. Or if you deliver, you don't know exactly how much they need that day. So you may give them a bit more or a bit less, bananas, for example. The travel times are stochastic. You don't know how much it takes to drive. And the difference between the stochastic demands and stochastic travel times is that stochastic demands tend to be independent of each other. Travel times are not independent. If there's congestion on one street, it's likely to be congestion on the next block. So it makes computations more difficult. And sometimes you have the presence of customers. You go somewhere and there's no one at the door and you've wasted your time. But that's more rare. So anyway, we've designed an exact algorithm for this type of problems with my colleague François Louveau from Belgium. And it's called the integer L-shape method. And it's an extension of Bender's decomposition to situations where you have integer variables in the recurse function. The recurse function is how much you pay if you fail to do something correctly. It's the backup solution. So you want to minimize the sum of the planned solution plus the cost of the backup solution if something goes wrong. So if you have traffic congestion, you may have to pay your driver overtime. That's a backup solution. So this is, so far, the only exact algorithm for these types of problems. And we've managed to solve pretty large instances, up to about 60 customers, with this variant of Bender's decomposition. Then, this is something that you know or should know about if you work in a university. It's examination timetabling. So at the end of each semester or each term or what have you, you normally have a week or two of exams. And you want to schedule the exams so that, first of all, you have a feasible schedule. What does it mean to have a feasible schedule? Well, you have no conflicts. You cannot put at the same time 2 exams for courses that have at least 1 student in common. Even only 1. You cannot put the 2 exams at the same time. Then there are room capacity constraints. There are various bizarre constraints. For example, sometimes exam A has to be before exam B. For example, if you have a chemistry course, very often the theoretical exam will be before the lab exam, that sort of thing. If you have a driving exam, you have to pass the theoretical test before the driving test normally, I think. So that sort of thing. And what is more important than feasibility is the spread of exams, controlling the spread of exams. It means the following. You don't want too many people to have too many exams in a short period. So if you have a large class of people, 400 students, who take 5 courses, so the same students take the same 5 courses, you'd like to spread the exams of these 400 students as much as possible so that they don't have too many exams in a row. So you want to spread exams as much as possible for as many people as possible. The consequence of that is that if you have a class of 10 students, these people get a very bad treatment in algorithms like this because the algorithm doesn't care much about them. But it does a good job for most people. So we solve this heuristically, and it's very simple. You do it with the computer like you do it by hand. How do you do it by hand? You take an empty grid. You take exam number 1, you put it somewhere. Exam number 2, you put it somewhere in the best place to minimize having too many exams together and that sort of stuff. And at some point, you take an exam, try to put it in the grid, it doesn't fit anywhere. So you have to undo a little bit of work you've done and carry on. Very simple. And in these things, we try to control very much the closeness aspect that I just described, either as part of the objective or either as constraints. And we've developed a software that's called Examine, and in the 1990s, by the way, and that won prizes and everything, and it was distributed in many universities in the world, mostly for free, and it worked for a while. And then universities started going to platforms like PeopleSoft and SAP and what have you. And these big systems that you use in universities to do your finance, to do your manpower management, everything, it includes very often a part that does the exam schedule. And universities don't like to have a separate exam scheduler. They like to use the same system for everything, without modification if possible. So that's dying slowly. And now districting. So you have a territory, and you want to partition the territory into small districts for various purposes. For voting. I think here you have the same system as in Canada and UK. We vote for members of parliament in separate districts, and the party that has the most winners is elected. I think that's the way it goes. Okay. So you want to design these districts so that the process is fair. So ideally, in an electoral context, you want the constituencies to have about the same number of voters, but there's always a margin of tolerance. You want the districts to be compact, as opposed to what you see here, to avoid what we call gerrymandering. Gerrymandering is a common practice in the United States. And this is why the system is so skewed and unfair. And this is why the Republicans typically win with much fewer votes than the Democrats. So you have to be careful about this. You want, of course, the constituencies to be contiguous in one piece and that sort of thing. So again, it's an easy problem to solve. What you need is to have basic units, little pieces. What is a basic unit? It can be a census tract. It can be a postal code on which you have statistical information. And then you want to agglomerate these basic units into larger districts that satisfy some criteria. How do you do it? Well, you initialize various districts on a plane, and you keep adding basic units to every partially designed district, and then you do some exchanges to improve the quality of the solution. Very simple, very, very simple. We did that for the city of Edmonton in Canada. So on the left, you see the basic units. You don't see the districts. On the right, you see the solved problem. You have 12 districts. And if you look at these districts, here they have to follow a rule. They could not overlap the river. So all districts except number 4 do not overlap the river. Number 4 is not so important because it's an almost rural district, and they didn't care too much about that. But in the city, they didn't want districts to overlap the river. If you look at this, the districts are reasonably compact. They have a sort of square or round shape. They're not like the animal I showed you in the previous slides. And of course, you cannot see it here, but they have about the same number of voters, the same population, and this and that. So this is a perfect solution. We did that, and it was adopted by the city of Edmonton in 2009, I think, and we won a prize for that in 2010, Best Canadian OR Society application or something like this. Then is waste management. So it has to do with rubbish collection. And if you read anything about rubbish or garbage collection, it's often presented as what we call an arc routing problem. So what is an arc routing problem? An arc is a street segment. And you want to traverse various street segments in the cheapest possible manner. It's different from the vehicle routing problem. Vehicle routing problem is a node routing problem. You have to visit nodes. But when you collect garbage, you have to visit the edges, the arcs, the streets. And it's more complicated than the vehicle routing problem. But it's not only that. Garbage collection is a lot more than arc routing. And there are all kinds of features that you have to take into account. First of all, you have to design districts. You have to give each district to a separate company or a separate truck or something like this. You have to locate facilities. What are facilities? Well, a depot. You have to locate dumps and what have you, recycling centers, and it's complicated. And as you see on the picture, garbage is not what it used to be 50 years ago. 50 years ago, there was only one type of garbage. Now there are many, many, many types. So that has to come into account. There's scheduling. You have to tell the people on which day their garbage is going to be collected. And with all these types of garbage, it's complicated. You cannot say, well, collect the garbage on Tuesday. No, on Tuesday is the paper, and on Wednesday is the food, and on Thursday is the plastic, and it's like that. And some of these types of garbage don't have the same frequency. For example, the general garbage that includes food and what have you, it's once a week normally. But metal, you don't have enough metal to throw away each week to justify a collection. So you can say the metal is once a month, once every 2 months. And the paper is once every 2 weeks. You have to think about that. And there's a vehicle fleet composition in the sense that there are various types of garbage trucks these days. Some are back-loaded, some are side-loaded, and so on and so forth. So you have to, some have compartments. So you have to decide, at the same time as you decide the schedules, which type of vehicle you're going to send to collect the garbage. There's some inventory control in the following sense. In some cities, maybe not here, but in Europe, you have these big bins that are put in the center of villages where you go and throw your garbage in. And some of these bins have sensors. And when a sensor tells you the bin is almost full, well, you know you have to go next day or the 2 days after. So there's some inventory management involved sometimes in these problems. And these problems are big, they're difficult to solve, you can only use heuristics. And you'll never know exactly how good the solution is, but you can make estimates. So this is some work we're doing now on precisely determining the fleet composition that's best suited to a certain situation. And some of these trucks have side compartments. Some have compartments on the two sides, which is nice, and some have compartments on the one side. So when you have compartments on one side, you have to take that into account to decide on which side of the street you travel and that sort of stuff. So we're working on this, not finished this. I'm doing that with my colleague, Annie's Bib. And another topic I've worked on a lot is metro network design. So suppose you have a city. Is there a metro in Melbourne? No, I don't think so. Yes, there's a metro here? Yeah, okay. So suppose you have no metro, you want to design a metro system. How do you do it? As simple as that. Where do you put the lines? It's difficult. So you certainly have to take into account where people live, what are the high density areas of your city, where people work, what are the important locations in the city, like universities. If you have a metro system, you'd like it to reach the university campuses, the tourist centers, some hospitals, and that sort of stuff. So you have to take that into account. And you have to understand how people travel. What are the flows of travel? People don't travel normally between two suburbs. They travel between where they live and the center of the city, something like this. Okay? So you have to think about that. You have to make sure that the trips that people make will not have too many transfers. You want to make sure that the trips that people make correspond more or less to what would be done on the ground. You don't like people to travel all around the place from that thing. It's complicated, and beyond all the combinatorial aspects that I'm describing to you, there are things that are engineering problems. These metro systems cost a fortune. There are always, always, always major cost overruns, because when you start digging, you never know what will happen. There are accidents. There are many players involved. It's not one person who decides, certainly not me. Okay? So you have many levels of decision makers, and there's no way that by writing an algorithm and pushing the green button that you'll find a solution. Forget about that. So what can we do? Well, as operations researchers, I think we can help generate good solutions. We can help evaluate good solutions. We can produce many solutions. We can solve some specific aspects of the problem. But you will never be able to solve the whole problems all at once. Forget about that. So we've worked on that, I would say, from 1993 till now. Never stopped. So I've been working on this for 30 years. And this problem will never be solved perfectly well, but we learn a lot. Typically, you will start with a basic structure that you'd like to have. A very good one is the middle one, what we call the cartwheel. They have that in London. They have the circle line, and they have lines intersecting the circle line. They have that in Moscow. The star, is a bad design, because you always have to transfer in the middle, and you get a very crowded station in the middle. This is bad. The triangle is not too bad, but the best design is the cartwheel, and of course, variants of the cartwheel, imagine. But if you've been to London, presumably most of you have been to London, you've seen the beautiful system they have. It's a cartwheel with many, many branches intersecting inside and between each other. They have a high connectivity level in London. So you start like that, and then you play a little bit with the branches. You move them left, you move them right, to cover people, to cover trips and that sort of stuff. But you have to start somewhere, and you play, and it's heuristic. Then green transportation. So the question is, how do you design green solutions to transportation problems? And this is some work that started with a problem we had in the shipping industry. You have these ships that have a predefined route. There's a ship that has to go from 0 to 4, and it stops at port 1, port 2, port 3, and finishes at port 4. So far, so good. And these ports have time windows. And this is serious. When you tell a port, I'm going to arrive at 9 o'clock, between 9 and 11, and if you arrive earlier, you have to wait because the berth is not available. And if you arrive later, you pay a fine. So there are all kinds of rules about that. You have to arrive within the time window, no joke. And if you don't, you pay a fine. And if the port is not available, if the berth is not available when they said it would be, the port pays you a fine. Okay? So what is the problem? At what speed should you travel so that you will always arrive within the time window of a port, and that you will minimize your fuel cost? So what is the fuel cost? Fuel cost is related to speed in a cubic manner, almost cubic manner. It's like any energy consumption. If you put your thermostat to get a warmer home, the cost you pay, the extra cost you pay to get warmer is cubic. Think about that. So how do you decide on the speed of on each segment so that you always arrive within the time window and you minimize your cost? Very simple. It's a cubic function. So we solve this problem for any convex function, which is nice. And we solved it exactly with an algorithm that takes O of n squared complexity, n squared, n being the number of ports. So we started like this and published that in Networks. And then with my colleague Talga Bektash, we worked on a more general problem. It's what we call the pollution routing problem. So if instead of minimizing the travel length of a vehicle, you want to minimize the cost or the pollution, how do you do it? How do you measure pollution? Well, pollution is proportional to the amount of fuel you use. And the amount of fuel you use is a function of the distance you travel, the speed, and the load you carry, and other stuff. Slopes, whether you put air conditioning or not, whether you open the window or not, and all kinds of stuff. But essentially, we made it simpler. We said, okay, it is a function of this, it's a coefficient times load times distance plus the square of speed times distance for certain ranges of speed. It's about that. So what does it mean? If I want to deliver goods, I have to solve a vehicle routing problem or a traveling salesman problem on this graph. Well, the cheapest way to do it in terms of length is to go from 0 to 1, 2, 3, and 0. You agree? Go around. Or I can go to 0, 3, 2, 1, and 0. I can do it clockwise or counterclockwise. It's the same distance. Suppose the speed is the same. Speed is constant. So I only have distance and then load. I want to deliver stuff. I want to deliver Q1 at number 1, Q2 at number 2, and so on and so forth. And I want to minimize the pollution cost. Well, the best way to do it is to deliver, to carry more weight on short distances and less weight on long distances. So at the beginning, I'm full. I have in my vehicle 0.25 plus 3.25 plus 0.25. I have 3.75 to carry. How should I start? Should I go from 0 to 1 or 0 to 3? Let's go from 0 to 3 with a big weight on a short distance. Then I go to number 2, number 1, and 0. But if I start with 1, 2, and 3, I carry more weight on longer distances. So it's the same distance, but if you take the weight into account, it's not the same cost. Now, suppose that I want to optimize that more fully. The best way to do it is to go from 0 to 2 directly. Get rid of the big weight, and then continue. So it's not the shortest distance. Now, suppose I have time windows. How do I do it? Well, how many solutions are there? 0 is fixed. There are 3 nodes to visit. There are 3 factorial routes, 6 routes. And I could do, like I did earlier with the boats, I can consider separately the 6 permutations and adjust the speed on each of these permutations and find the best solutions. But it's stupid to enumerate everything, so we have to use integer linear programming, and that will do the job. And then electric vehicles. There are other problems induced by that. They have batteries instead of fuel tanks. So the question is, when do you recharge the batteries? How much do you recharge them? Where do you put the recharging stations? You have to understand that it takes a lot of time, first of all, to recharge a battery. There are some quick technologies that are very expensive, and there are some slow technologies that are relatively quick. But would you recharge your battery fully if you don't need to? Maybe you should just do what you need and come back home, come back to your depot, and continue the recharge after. You should never recharge a battery more than 90%. It will damage it. You should not recharge it too often. It will damage it too. So it's full of questions you can ask regarding how much you recharge your battery. Some companies recharge their vehicles at the depot during the night when they know that they can have enough power to do their job during the day. So they don't go to public charging stations. They do it at home. There are technologies where you can exchange batteries. It's very good to exchange batteries if it's on your own fleet and your own batteries. But if you have a car, would you go to a station where you give your battery that's been well maintained and you get some cheap battery in return? You don't know what you get in return. Would you trust that? And what if you're traveling in some remote place like the outback here, and you go to a swapping station, and they say, sorry, mate, we don't have a battery for you today. Come back next week. Good. So we worked on this. We had a very good student, Samuel Petit. He did his thesis on this. And before I go to number one, here's a little joke. So these are two dartboards. The one on the left is a standard dartboard that you see everywhere. And the one on the right is an optimized dartboard done by my colleague Eiselt and me. So what are we optimizing? We're maximizing the risk. We want to make the game as complicated as possible. So if you aim for number 20, you may hit number 5, number 1, with some high probability. And we want to put next to 20 two very small numbers to make your life difficult. So how can you optimize that? Essentially, it's a traveling salesman problem. So we did that. And we obtained an optimized dartboard with a risk level of 2,642. Well, I don't have to tell you how it's computed, but it's very simple. It's a kind of variance stuff. And the one on the left is the official dartboard, which has quite a good risk level. It's quite tough too. It was designed by hand by an English guy in 1896. And it's not bad in terms of risk. And it is, in fact, nicer than the one we designed. It's more irregular, less predictable. The one on the right is a little bit too predictable. The one on the left is nice. So we did that, but that's not the end of the story. We published that in the Journal of the OR Society in England, and we received a nasty letter from some president of the Dart Society in the UK. They take Dart very seriously in that country, I tell you. And the guy said, we had no right to change the rules of the game and blah, blah, blah. We knew nothing about darts and all kinds of stuff. I wanted to display this letter, but I couldn't find it after so many years. But the guy was not very happy with us. I tell you. And then this is my last topic. It's one of the several topics I've worked on in humanitarian logistics. This one has to do with the location of water taps in Nepal, where they had 2 big earthquakes in 2015, and the whole water network distribution was broken, and they had to start again. So what you want to do essentially is to locate water taps in villages that need them. It's a location problem, it's a covering problem. You don't want people to walk too much to reach a water tap. And once you've decided where to locate the water taps, you have to connect these water taps by a tree. In fact, it's not a tree, it's a forest, it's many trees. And there's an additional feature. You're not allowed to use electricity. You're not allowed to use pumps. So everything has to be natural. Everything has to be physical. So you cannot, on the left picture, send water from the little river that you see on the left to the end place, because the water cannot go up. It doesn't have enough strength. Whereas on the right, it's feasible. So water can go up, but not to a large extent. And there are, believe me, equations regulating these things that have been found in the early 20th century by some physicists. So, 1933, but this is the third edition of their book. I think the first edition was 1914 or something like this. So we solved that. We did some tests in Nepal, and we work with the Red Cross societies of Austria, by the way, and Nepal, and we showed them our solutions, and that will guide them towards restoring the network, but it's not done yet. So this is that, and what can I tell you? After 50 years, I started my life as a student in mathematics. I wouldn't say as a mathematician, as a student in mathematics. When you're at school, it's quite easy to be good in mathematics. But when you reach university, you find that mathematics is a lot more than calculus and automatic things. It's very, very abstract. And I didn't want to have a career in mathematics. I said, I'm not made for that. I want to do something a bit more applied. So I decided to go to operational research. I went to England, to Lancaster, then to London School of Economics, where I did my PhD with Arzalan. Have you heard of Land and Doig? Yeah? Well, I was with Land. And Alison is my aunt, my scientific aunt. So I went to work with Arzalan, and I never regretted that choice because OR is so rich. It's a field where you can do what you like. You can do theoretical things. You can work on computer applications. You can do applied work. You can do consultancy. You can do mathematics. You can do what you like. There's no limit. And the number of applications is huge and non-ending. Huh? So if you want some advice, I would say work on problems you like, whatever your field of research. Work on things you like. And develop cooperations, I would say. I have over 400 co-authors. It's a lot of cooperation. And if you teach, it's nice to be able to connect your research to your teaching. It's not always easy when you teach in undergraduate classes with 400 students, but even then, when you teach basic things, you teach probability, you teach statistics, you teach linear programming, you can tell the students some applications of that. It's not just stuff to learn by heart. It's useful what you're doing. So bring your research in the teaching and you'll be happy. So I think that's the end of my presentation. I said 1 hour, and that's about it, I think. I've lost the time.